Okay, welcome everyone. So today is my great pleasure to introduce Shubhadeep from Biostatistics Department. Shubhadeep is currently a postdoc researcher working with Professor Ali Chaudhry and working on all kinds of very exciting topics, including non-parametric statistics, high-dimensional statistics, causal inference, and change point detections. And Shubhadeep got his PhD in statistics from Texas A&M and working with Xiangyang Zhang and before that, he actually received a master's degree from Indian Statistical Institute in 2015. And today he's going to talk about a very exciting topic about high-dimensional change point detection. So welcome, Steve. By the way, you have for audience who are new here, so you have 3 ways you can ask questions. The first one is that you can use raise your hand function, and Christine and I will be monitoring that. And if you raise your hand, we'll allow you to speak. And you can ask questions directly, or you can just type your question in either the chat box or Q&A. Okay, so without further ado, let's start.
Thanks, Yanchi, for the nice introduction and also for inviting me here. Let me quickly share my screen. Can you see, is my screen visible?
Yes, it's visible.
Oh,
yes.
Awesome. The topic of my talk today is on high-dimensional change point detection using generalized homogeneity metrics. And it's a joint work done with my PhD advisor, Dr. Xianyang Zhang at Texas A&M University. Change point detection is a classical and well-established problem in statistics and econometrics. It has a long history, finding its origins in quality control, and has remained an active area of research till today because the phenomenon of sudden changes arising in sequentially observed data arises. We commonly encountered them in a lot of applications, like in finance, in bioinformatics, in neuroscience, social network analysis, and so on. Towards the end of this talk, I will talk about an application or a change point detection problem in case of stock prices data. So essentially, change point detection is all about detecting if there is some change. The change might be with respect to the mean, covariance structure, the underlying distribution, along a sequence of time-ordered observations. So in recent times, there have also been works on detecting changes in the structure of time-varying networks. There's a vast literature on change point detection, mostly in the context of detecting a change in the mean or the covariance structure, and mostly in the low dimensional or the univariate context. But recently, there have been more and more works in the high dimensional framework as well. So as we are in the era of big data, high dimensional data are now commonly produced in many scientific areas such as neuroscience, genomics, finance, among many others. So one major challenge that the researchers today have to face while trying to develop change point detection methodologies is to tackle with the high dimensionality. So there has been a host of recent works in detecting a mean shift or a change in the mean for a sequence of high dimensional observations. So just to mention a few, there has been some annals papers by Enikiva and Harchawi 2019, a 2015 annals paper by Chirac, some JRSSB papers, Cho and Fryzlewicz 2015, Wang and Samworth 2018, or just to mention a few. Compared to the literature on detecting mean change, the literature on detecting covariance change, especially in the high dimensional framework, has been relatively less. But in the recent times, there has been some prominent works by Avanisov and Buzun, a 2018 EJS paper, and 2020, a very recent JASA paper by Data and co-authors, and so on. So the point is, the literature till date on developing general non-parametric methods to detect general kind of changes in the distribution, in the underlying distribution of the sequence of data observed, is relatively scarce till date. To the best of my knowledge, there only exists just a couple of or 3 or 4 papers on this topic on detecting general changes in beyond the first 2 moments in the sequence of high dimensional data. So one of the pioneering works is a 2014 JASA paper by Mattison and James, who proposed a methodology for detecting an unknown number of multiple change points in a non-parametric setup based on energy distance. Well, in a minute, I will talk about what is energy distance and also some of its limitations when dimension grows high. So I will come back to this point later, but for this point, at this point, I would just like to mention that the change point detection methodology developed by Mattison and James, it does run into some problems when dimension grows high. There have been some graph-based tests proposed by Chen and Zhang in a 2015 Annals paper, but it has several limitations. Like it can, first of all, detect only 1 or 2 change points. It is more effective to location alternatives compared to scale alternatives. And the third is that, so when the true change point is not anywhere near the middle of the sequence of the data observed, it performs poorly, or it has low detection power in estimating the single change point location. So as an improvement, Chu and Chen came up with a 2019 paper which improves these limitations to some extent. The graph-based test proposed by them is powerful for both location and scale alternatives. But in our extensive numerical studies, we show that these graph-based tests, they perform poorly in detecting changes in higher order moments. So the goal or the motivation of this work is how to detect general distributional changes in a sequence of high dimensional observations. So the key to answer this question is, how do we compare to high dimensional distributions in the first place? So just as a quick summary of our contribution, the problem that we consider is to detect general changes in a sequence of high dimensional time ordered data beyond the first 2 moments. And we develop a non-parametric methodology to detect an unknown number of change points. And once we estimate a candidate change point location, we test for the significance of the estimated change point location. So that's kind of the broad goal of the talk that I'll be talking about today. So to begin with, I'll first give a brief overview of energy distance. Energy distance is a non-parametric, it's a homogeneity metric which is aimed to capture the equality of 2 distributions. So let's see how it is defined. Let's say X and Y are 2 p-variate random vectors. Suppose X and Y are independent and with finite first order moments. So energy distance proposed by Shekli and Rizzo in a 2004 paper is defined like this, as kind of a weighted L2 norm of the difference between the characteristic function of X and the characteristic function of Y. So what is immediate from the definition of energy distance is that if X and Y are identically distributed, then their characteristic functions should match almost everywhere, making this quantity 0. On the other hand, if this quantity is 0, because it's an integral of a non-negative function, so the characteristic functions of X and Y should be equal almost everywhere. So essentially, what is immediate from the definition is a complete characterization of equality of distributions. That is, energy distance between X and Y is 0 if and only if X and Y are identically distributed. So it's worth mentioning that there is an equivalent alternate expression of energy distance in terms of expectation of certain Euclidean Euclidean distances. And what's important about it is because of the presence of this equivalent expression, we can come up with some U statistic type or V statistic type estimators for estimating energy distance without having to trouble ourselves with estimating an integral like this. Well, then a question that will naturally arise here is that this characterization of in the expression of energy distance, if we replace these Euclidean distances by any general metric, does the characterization of homogeneity of distribution still hold good? So to answer that question, the answer is yes. So suppose consider a general metric K on the p-dimensional space. If this metric space has strong negative type, then the answer is yes. So I will not go into what is the definition of strong negative type, just to make the talk not very technical, but just for illustration, I would like to state that any separable Hilbert space has strong negative type. So in particular, if we consider Euclidean spaces with a L2 distance, then that's a Hilbert space, that's a separable Hilbert space. So the characterization of homogeneity of distributions when we use Euclidean distances is just a special case. The point is, until very recently, there has not been a lot of literature which discusses or tries to investigate how well do the homogeneity metrics like energy distance behave when dimension grows to infinity or in high dimensional frameworks. Is it still capable of capturing the homogeneity of two high dimensional distributions, or does it suffer from some limitations? So this wasn't addressed in the literature until very recently. In a recent paper, we showed that energy distance, all it can do, let alone capturing complete homogeneity of two distributions, all it can do is to test for the equality of the mean vectors and the variance elements of the two high dimensional random vectors. So I will talk more about that limitation of energy distance in just a couple of slides. But so the point is that, can we overcome at least partially some of those limitations of energy distance by replacing this Euclidean distance in the definition of energy distance by some suitable other appropriate distance metric? So with that in view, what we define is a metric on the p-dimensional space. So let's say x and x prime are two p-dimensional vectors. We define a distance k between x and x prime as essentially the square root of the L1 distance between x and x prime. I should state that in our paper, actually we propose a more broader class of metrics, but just not to make the slides look very technical and the talk very complicated, I would just focus on this special case and show how we can overcome some limitations of energy distance if we replace in the definition of energy distance the Euclidean distance. So in one of our recent works, we propose a generalized energy distance. Just like I said, in the definition of energy distance, replace the Euclidean distances by the newly proposed metric. So at this point, the first question I expect to hear is that, at least for the low dimensional case, just like the usual energy distance or the Euclidean energy distance, does this generalized energy distance still have the complete characterization of homogeneity? So the answer is yes. We could show that this metric K, it's a valid metric, first of all, and when equipped with r to the power p, it has strong negative type. So what essentially follows is this generalized energy distance has the complete characterization of equality of distributions, just like Euclidean energy distance in fixed dimensional case. So before going into how it behaves in the high dimensional framework, I should point out a few things, like what are the estimators of this guy. So keeping in view the form of the generalized energy distance, So suppose we have two samples, one on X, the other on Y. So we define an unbiased U statistic type estimator of the generalized energy distance in this way. And based on that, we define a two sample statistic. So which is defined in this way, like we are appropriately scaling this U statistic type estimator of generalized energy distance by its pooled sample variance estimator. So it's very similar to I mean, it's kind of similar to the two sample t-test for equality of means in case of equal variances. So coming to the asymptotic properties, which are actually very important. So we showed that under certain mild conditions, under the null hypothesis that X and Y are identically distributed, we showed that as the dimension grows to infinity, the two sample statistic converges weakly to a t distribution when the sample sizes are fixed, that is, which is popularly called the high dimension low sample size framework, and to a standard normal limit when the sample sizes grow to infinity as well at a slower rate than p, which is typically called in the literature as the high dimension medium sample size framework. So based on the limiting behaviors of our proposed two sample statistics, we propose a high dimensional two sample test for the equality of two high dimensional distributions, which we propose like this. So for any pre-specified level alpha between 0 and 1, we reject the null hypothesis if the value of this two sample statistic is bigger than the upper alpha quantile of the standard normal distribution. And I should also point out that the computational complexity of our two sample estimator, it grows linearly with the dimension. So now let me come to the really interesting question that how does energy distance behave in high dimensions, and how does our method or our generalized energy distance overcome some of its limitations? So we showed that as the dimension grows to infinity, via some Taylor's expansion, we showed that both the energy distance and the generalized energy distance, they admit the following decomposition into a leading term plus some asymptotically negligible remainder, where, very interestingly, for the Euclidean energy distance, the leading term is 0 if and only if the mean vectors are identical and the traces of the covariance matrices are the same. So it sends us a striking message that in high dimensions, the usual Euclidean energy distance cannot capture any inhomogeneity between two high dimensional distributions beyond the first two moments. So first of all, we believe it's a striking result which has not been shown in the literature earlier. And for our generalized energy distance, the leading term is 0 if and only if the univariate marginals of X and Y are identically distributed. So what does that mean? So that means, I mean, if the univariate marginals of X and Y are identically distributed, then for sure it implies that the mean vectors are the same and the traces of the covariance matrices are the same. So the takeaway or the bottom line from this discussion is that in high dimensions, the generalized energy distance can capture pairwise homogeneity of univariate marginal distributions beyond the first two moments, which is not achieved by the Euclidean energy distance. And it is powerful against a larger range of alternatives. In our paper, to be precise, we proved a more general result, but for the sake of simplicity, I just present this. So what we have talked about so far is what is energy distance, its characterization of homogeneity of distributions, its problems in the high dimensional framework, generalized energy distance that we proposed, its estimators, and how it overcomes at least partially some of the limitations of energy distance. So it remains as an open problem that, so if you ask a question that, well, then can we completely characterize homogeneity between two high dimensional random vectors? It's a very good question, but I don't have an answer at this point. What I believe is there might be some intrinsic difficulties in completely characterizing the homogeneity of two high dimensional distributions unless we impose some structural assumptions on the components of the random vectors. So just to give a brief illustration, just to end the discussion on energy distance and all. So let's suppose we are obtaining two samples, one on X, the other on Y. So the sample of on X is generated as IID normal with unit means and identity covariance structure. And for Y, we sample each of these components independently from an exponential distribution with unit mean. So clearly what we have here is that the mean vectors for both X and Y are identical and their variance elements are identical as well. But clearly X and Y do not have identical distribution. So we should expect that in this case, our generalized energy distance based test for high dimensional homogeneity of distributions should perform way better than the Euclidean energy distance based tests, which cannot capture anything beyond this in high dimensions. And that's precisely what we see over here. So it shows that, this table shows the empirical power over 1000 simulation trials. And we consider the sample sizes to be 50-50 and the dimension to be 100-200. We showed that the empirical power of the Euclidean energy distance based test is close to the nominal levels. So it clearly has trivial power in these kind of examples. So
there was a question from Wenyu. He was asking, what if P also goes to infinity and an N increase with respect to P?
N increases with?
So the dimension P also goes to infinity. So what will happen in that scenario?
So, this is, that's a good question. So we typically consider P going to infinity. And the limiting distributions are just different based on whether the sample sizes are fixed or they also go to infinity as well at a slower rate than P.
Okay, yeah, I think that's okay. Thanks.
Sure. Thanks for the question. So now with the background we have discussed on energy distance, now let us get back to the change point problem. So where I started from, if we still remember the discussion, I said that Mattison and James in a 2014 JASA paper, they proposed an energy distance based change point detection methodology. But as I mentioned at that point, that it should run into strong limitations in high dimensions. This is exactly what I mean. That energy distance, it cannot capture anything beyond the first two moments in high dimensions. So any change point detection methodology that uses energy distance to detect general distributional changes should not do well in high dimensions. So that's kind of what we want to achieve. So the point is whether we can use the generalized energy distance and prepare a non-parametric methodology for change point detection, which will of course improve over the energy distance based procedure for high dimensions. So let me first provide the statement of the problem. So let's say we have an independent sequence of observations, of p-dimensional observations. We typically consider the dimension to be higher than the sample size. And the null hypothesis is that all the observations follow the same distribution against the single change point alternative, which states that there exists a time point such that the observations up to that time point follow some distribution f naught, and the observations from tau naught plus 1 onwards, they follow another distribution f1, where f naught and f1 are two probability distributions differing on a set of non-zero measure. So the question is how to estimate the location of this tau naught. So to talk about that, I will first briefly talk about an intuitive idea that what we should do if we had to detect a change in the mean, not a general change in the distribution. So let's denote x1 to k as the observations x1 up to xk. So in the change point literature, one usually defines a cumulative sum process or CUSUM process, which is defined in this way, which after just a few algebraic manipulations can be shown to be some suitable weight function in terms of k and n. And so k is just a point. So what sk computes is that it splits the entire range of the observations into two segments, one to the left of the position k and one to the right of the data point xk. So we compute the means of the observations to the left and to the right of k and take a difference of the two. That is how sk is defined. So for each k from 1 to n minus 1, we keep observing the differences of the means for the two samples to the left and to the right of it. So a natural statistic to consider is the maximum value of the squared norm of this sk. So whichever is the maximizer of the squared norm of sk, or in other words, whichever k maximizes the squared norm of sk, we can call it a candidate change point location, which of course needs to be tested against a certain threshold to declare it to be a significant change point location. But that's roughly the intuitive idea. So now that we have a setup where we want to detect general changes in distribution, so instead of considering this difference of means, how about we consider the two sample statistic that we just talked about based on generalized energy distance for the two samples, one to the left of xk and one to the right of xk. So that's kind of the idea. And so the maximizer of these ones, we call it the candidate change point location, tau naught hat. Of course, it needs to be tested whether it's a significant change point location or not. So how we can do that is, so whichever k maximizes this guy, we look at the value of qn and we look at whether qn exceeds a certain threshold. So how do we get that threshold? For that we need to find the limiting distribution of this guy qn, which may not be trivial, and it very much depends on a suitable choice of a weight function. For example, Mattison and James in the 2014 paper, they considered qn to be the maximum of energy distance, just the simple Euclidean energy distance between the two samples x1 to k and xk plus 1 to n with this particular weight function. So that's kind of the intuition of our methodology. So what we propose is, we propose a candidate change point location estimate to be the maximizer of this guy, where this is, as I said, just the two sample statistic based on the generalized energy distance, along with a suitable or appropriate weight function. And the maximum value is given by mn, which needs to be checked that whether it exceeds a certain threshold in order to claim that this candidate change point location tau naught hat is a significant change point location. So just a quick thing to point out that we have 4 and n minus 4 here because the computation of the statistic takes at least 4 samples on each side. And the key challenge in coming up with a test based on this is that we first need to rigorously derive the null distribution of mn, which has been our key theoretical innovation. It has been non-trivial because in order to show or establish a weak convergence result for Mn, one needs to uh, first establish a uniform weak convergence result for these T, which requires finite dimensional convergence and stochastic equicontinuity. So let's consider K to be the greatest integer less than nr, where r is some fraction. So the first theoretical result that we show is that this stochastic process, it converges weakly to a non-pivotal and distribution-free limit uniformly over R, which I mean, and just as a corollary of this theorem and using continuous mapping theorem, what we get is that when the dimension grows to infinity and the sample size also grows to infinity at a slower rate under certain mild assumptions, we show that this statistic Mn, it converges to a pivotal and distribution-free limit. So based on that, what we can do is, as I said, that we need to see if Mn exceeds certain threshold or not. So what we need is to approximate the quantiles of this limiting distribution of Mn. So for that, one can approximate the quantiles of the limiting distribution, given that it's distribution free, via a large number of Monte Carlo simulations. That's one way. We used a permutation procedure to approximate the quantiles, hoping to achieve more accurate results. So the single change point detection procedure, we state it like this. So for any pre-specified level alpha, we say that a candidate change point location tau naught hat is significant if Mn exceeds the upper alpha quantile of its limiting distribution. And so that was kind of our methodology for single change point detection. And when we have multiple change points, which arises commonly in practice, which is very natural, that we consider this multiple change point alternative, which says that there exists some integer n such that there exists some locations tau1 up to tau n, for which the first tau1 observations follow some distribution f naught. The observations from tau1 plus 1 up to tau2 follow a different distribution f1, and so on. So very naturally, both n and these tau1, tau2, tau n both are unknown, or in other words, the number of true change points or the location of the true change points both are unknown to us, and we need to estimate them both. So basically, we need a greedy procedure to sequentially detect multiple change point locations based on our single change point detection procedure. So one of the very popular ideas or strategies to search for multiple change point locations is the idea of binary segmentation. So how that works is, suppose this is the sequence of observations. So firstly, for the entire sequence, we implement the test for a single change point location. Suppose this turns out to be a significant change point location. Then based on that change point location, split or segment the entire data sequence into two segments or two sub-intervals. So hence the name binary segmentation. So for each of the bisected sub-intervals now, keep continuing the procedure until no further change point is detected. So that's kind of the overall idea of binary segmentation. However, in 2014, in an annals paper, Fryzlewicz came up with a modification of the binary segmentation called the wild binary segmentation, which does a modification to the binary segmentation procedure, recursively trying to detect multiple change point locations. So I will briefly just state what does a wild binary segmentation do. So instead of, so let us focus on the first step. So in binary segmentation, one would apply the test for single change point location on the entire data range. Instead of doing that, what wild binary segmentation or WBS does is from the entire data range, it selects a lot of, a large number of sub intervals randomly. For each of those sub intervals, compute MN. So it's like instead of computing MN for the entire data set, select some sub intervals. For each one of them, compute the value of MN. And over all the intervals, whichever is the largest maximizer, choose that to be the candidate change point location. And of course, that needs to be tested against a certain threshold. So that's the key difference between binary and wild binary segmentation. And then the recursion is exactly the similar. If we find one candidate change point location to be significant, then bisect the entire interval into two parts, to the left and to the right of it, and keep repeating the procedure recursively until all the change points are detected and there is no further change point. So one quick question you might ask is why do, it seems like binary segmentation is computationally much less intensive than wild binary segmentation. Then why does one bother oneself to go through wild binary segmentation? There are several answers. One answer is that for detecting some change point, it requires to look at a narrow interval around it. So if we do wild binary segmentation and keep doing this random selection of sub intervals, there is a positive chance that those change points get detected. Another answer is that improving the consistency for the binary segmentation or the wild binary segmentation procedure for consistently estimating multiple change point locations. For the binary segmentation, it is necessary to assume that the minimum spacing between two adjacent true change points is quite large. So that's another advantage. And for wild binary segmentation, it's relatively much smaller. So there are some advantages of WBS, although it is computationally more intensive. So now let me just provide a brief illustration of some of the numerical studies that we performed. As I said, the competing methods that we compare our methods with is, one of them is the Mattison and James paper. The other two are the graph-based approaches by Chen and Zhang and Chu and Chen. And we also compare our methodology with the inspect procedure proposed by Wang and Samworth in a 2018 JRSSB paper. So I should mention that this is a paper which is meant to detect mean shift for high dimensional data. So why do we then compare it with ours? That is because we just want to make it clear that our methodology detects changes in detects general changes beyond the first moment. So let me go over some numerical illustrations. In the first example, it is an example where there is no structural break. That is, all the observations x1, x2, xn, they all come from independently from a multivariate normal with zero mean and identity covariance matrix. In the second example, we consider a single change point in mean. So the first half of the observations, we draw them from a zero mean multivariate normal with a AR1 covariance structure. And the second half of the observations, we draw them from a bivariate normal with the same covariance structure, but with a slightly changed mean. So this is the table showing the average values of adjusted RAND index for the different methods over 100 simulation trials. So what we do is, based on the change point, significant change point estimates, we clustered the observations according to that. And what the adjusted rand index does is, so the value of the ARI is between 0 and 1. It takes the value 0 if in either of the two cases. The first case is that there is no true change point and the method detects one or more change points. In that case, ARI would be 0. Also, if there are actually one or more change points, but the method fails to detect any, in that case also ARI is going to be 0. And the average rand index is going to be 1 if the estimation of the change points is perfect. So higher the value of ARI, better is the better is the estimation procedure. So we use sample size 100 and dimensions 100 and 200 at a significance level of alpha 0.05 and 199 permutation replicates. So we can clearly see that nearly all the methods, they perform equally good for both the case when there is no structural break and when there is a single change point in mean. Just that Wang and Samwart's procedure, it turns us out with a 0 ARI value, because even when there is no structural break, it detects 1. So other than that, for the single mean change case, it is intuitive that all of them would work good, because Wang and Samwart's method is meant for detecting mean change for high dimensional data, and example 2 is essentially on detecting a mean change. We said that the graph-based methods by Chen and Zhang and Chu and Chen, they are powerful against location alternatives, so it's no wonder that they do good. Mattison and James's procedure, we say that in high dimensions, all it captures is changes in mean and the variance elements. So again, it's no wonder that Mattison and James method will do good in this case. The real interesting thing comes when we talk about single change or multiple changes in higher order moments. So we talked about this example before. Let's suppose in example 3, what we do is the first half of the observations, we draw them from multivariate normal with unit mean and identity covariance matrix. The second half of the observations, we draw in a way that the components of X are identically distributed independently as exponential with mean 1. So again, just like we discussed before, that the mean remains exactly the same, and the variance elements again remain exactly the same, but there is indeed a change in distribution at this point. And in example 4, we consider 2 change points. So the first and the last 1/3 of the observations, we draw them from multivariate normal with unit mean and identity covariance structure. And the middle 1/3, we draw it from the exponential distribution. So let's see how our method performs compared to the other state-of-the-art methods. So we consider again the sample size 100 and dimension to be 100 or 200. First of all, the method by Wang and Shao, it doesn't do great as expected, because the change is not in the mean, it is in higher order moments. The graph-based tests by Chen and Zhang and Chu and Chen, they also don't do great. Again, as I mentioned, that they are powerful for location and scale alternatives, but they do not do great if the change is in higher order moments. Mattison and James test, again, it also doesn't do great. Again, it was expected because of the limitations of energy distance and the fact that it uses energy distance to detect changes in the distribution in high dimensions. Our test outperforms all the others in terms of the average value of adjusted rand index. So I will stop with a quick application to stock prices data, which is quite interesting. So we consider stock prices data for corresponding to 72 companies under the consumer defensive sector during the time of the Great Recession in the US. We observed data on the first dates of each month between 2005 and 2010. So the motivation is that when a recession occurs, the markets tend to become volatile and prompting the investors to sell stocks. Although all the industrial sectors are susceptible to economic changes, but there are some sectors which are relatively more robust or resistant or less sensitive to a recession. For example, say healthcare or utilities or consumer defensive. And there are some sectors which are more susceptible to a recession. For example, finance or real estate or oil and gas, automobiles, these kind of sectors. So the goal is, if we choose stock prices corresponding to companies that are that fall under a relatively more resistant sector to recession or economic slowdown, then can our change point detection methodology and the other state-of-the-art methods, can they detect change points from the stock returns data? Just to state some facts, the Great Recession officially began in the United States in December 2007 and lasted till June 2009. So it's around 19 months. The government responded with a $700 billion bank bailout in October 2008 and a $787 billion fiscal stimulus package in February 2009 to save the economy. So what we observe is our method detects two change points. One in September 2007 at the beginning of the recession. The other is at January 2009. Keeping in mind the historical sequence of eventualities that the financial packages being offered in October 2008 and February 2009, it seems quite reasonable. And about the other competing methods, Mattison and James's procedure fails to detect any change point. Wang and Samwart's procedure detects as many as 18 change points during that time frame. Chen and Zhang's method detects only one change point at March 2009, and Chu and Chen, their procedure detects two change points, one in May 2008 and one in September 2008. So for illustration, I include time series plots of stock returns for 6 companies under the consumer defensive sector. So the red solid lines are the change point estimates detected by our method, and we can clearly see that there is a dip in the stock returns data within these two timelines, and these dotted blue lines are the change point estimates determined by Chu and Chen, and this gray dotted line is the change point detected by Chen and Zhang. So to finish my talk, just a couple of discussions on what can be some potential topics for future investigation. It is indeed a very interesting topic with plenty of open questions. And for example, one question is that how to, so in developing our methodology, we developed it for an independent sequence of time ordered observations. Well, in many practical applications, the observations might have some temporal dependence. So a question is how to extend our methodology for multiple change point detection in case of a weakly dependent high dimensional time series. So that's a intriguing question, but this seems absolutely non-immediate and non-trivial from both methodological and theoretical perspectives because of the simply because of the additional complexity brought in by temporal dependence. Number one. Number two is that how to develop consistency results for the wild binary segmentation procedure we implemented in the paper. So this again looks technically non-trivial because in the 2014 Annals paper by Fryzlewicz, where he came up with the idea of WBS. So he proved consistency results for the wild binary segmentation procedure. but that was in the context of detecting a mean change, and that too for univariate sequence of observations. So extending that to the high dimensional framework and for detecting general distributional changes doesn't look quite trivial. And that question still remains that, so what our generalized energy distance or a change point detection methodology based on that is capable of doing is detecting a change in the univariate marginal distributions of the components. So can we go any further, and can we come up with, in general, a homogeneity metric that completely characterizes the equality of two high dimensional distributions, and then framing as a next step a change point detection methodology based on that. That's something that we are already working on. So these are that was kind of all. So this is the paper which I referred to. I mean, this is our recently archived paper for the change point detection method, and this is one of our previous works where we came up with the idea of generalized energy distance. And these are some of the other references that I mentioned. So thank you very much.
Okay, thanks, Steve. Very nice talk. And I saw a question from Zai.
Sure.
So yeah, maybe I can allow Zai to talk. Zai, I think you should be able to ask question directly.
Right. Yeah. Thank you so much for the great talk.
Thank you.
Yeah. So so this is an interesting work. There is a striking resemblance with kernel-based metrics that were proposed for change detection like almost 14 years ago, and I was wondering how do these methods compare to kernel-based change detection approaches? Because there's a similar CUSUM statistics in Hilbert space. The distribution is very similar, and also I think when you have multiple change points for kernel methods, there was a dynamic programming procedure that was proposed, and so I'd like to hear.
Thanks for bringing up this question. I mean, we didn't consider comparing with kernel-based approaches. So the papers that you were talking about, are they on in the high-dimensional context?
Yes, there are non-asymptotic bounds that hold for any dimension, any sample, and in fact any metric space.
Say that again. I missed you for a moment.
They hold for any sample size, any dimension, and any space, any data space equipped with a metric. So they so there are both asymptotic works and non-asymptotic works. Yeah.
I see. No, we honestly, we haven't compared with the kernel-based approaches. I mean, the one thing that I have in mind right now after hearing your question is that, so in our previous paper, we showed that, or in some recent works, it has been shown that both distance covariance and Hilbert-Smith's independent criterion, because they're connected, they both suffer from some limitations in the high dimensions. And that was our motivation, that whether MMD or energy distance, which are again connected, I mean, they both of them have some limitations in the high dimensions. So when it comes to high dimensions, I believe, I mean, whether we need to I mean, do some modifications on the popular kernel or distance-based metrics or the change point detection methods based on them for the high dimensional setup. So, yeah, so that is one thing I think we need to look at.
Yeah. Okay. Yeah, we can take the continuation of the discussion offline. Thanks.
Sure. Yeah, thanks very much for the question.
Okay, thanks. And I think I have a question from David. David was asking, in your papers, do you handle the fact that you're estimating your change point with the entire data set, and then you reuse the data again to test the significance of the change point?
Yes. So basically, let me show. Yeah. So For the entire data set, we are estimating a change point location and testing for its significance. Then we are visiting this particular interval and that particular interval. And again, estimating and testing for the significance of any change point locations presented over here and there. Yeah, that's how the procedure goes.
Nice. And while others might be thinking about questions, I find this topic very interesting. I have one very simple questions, and
sure.
I'm just curious. Do you have any characterization about like thinking about in terms of the power analysis, that kind of problem? Because I think NumPy tells you that in your methods, like what would be like it try to tell the distributional changes, right? So sometimes the power might depend on certain characteristics. There's like sometimes it's like for simple problems, like the mean difference, but sometimes it might be some Hellinger distance between the two or some other distance metrics measuring that. So I'm just curious, like have you have some theory on the power analysis that kind of tells you actually what is really the driving factors about like inside the method? Although I believe that it might actually depends on the kernel function you were using.
Yeah, that's a great question. I mean, I think the key lies here. So here I didn't quite show some derivations, but I mean, I'll be happy to share my. It's available on archive though. So when we do some Taylor's expansion, when we expand these homogeneity matrix, I mean, the same thing happened for distance covariance or similar things. So I think it's because of this decomposition. I mean, so just to see what does this leading term capture, and the remainder, of course, is negligible. So I think this is the key to look at. I mean, when you talked about power analysis, we had some numerical, so we had some theoretical results on the power studies for the generalized energy distance. But I mean, I think this is the key to look at.
Thanks, Dave. And other questions? Oh, yeah, there's another question from David. Is it possible to use your method to detect which moment change?
That's a good question. I don't have an answer with me at this point. No, I don't think so. I don't think so. I don't think it can detect which moment is changing. That's a good question.
Okay, thanks. And other questions? Okay. Well, it's right. So if no other questions, I think we all thanks Sudhir again. It's very interesting talk.
Sure. It was my pleasure. Thank you so much for the wonderful questions.
And thanks everyone for participating, and have a nice weekend. Okay, see you all. See ya.
Thank you.